Good morning everyone. Jai Hind. This is Dr. Shivani Agarwal. Today I am present here on the topic of instruction cycle, that is the topic of computer organization. The code of computer organization is KCS 302. So we start the presentation. Now, what is instruction cycle? Basically, every program or every instruction that inside in the memory, when we want to execute that instruction, so that instruction executes by the instruction cycle, because each and every instruction of computer consists of following phases of instruction cycle. First phase is the fetch phase. Second is decode, read and execute. So there are the four phases that we have to use for executing any instruction in the computer system. So these four phases are very important for executing any instruction in the computer system. So a program resides in the main memory of computer consists of sequence of instructions. There are many instructions in the program. There is not only the single instruction. So each and every instruction follow this particular instruction cycle for executing that particular instruction. So each instruction cycle in turn subdivide into the sequence of sub-cycle or phases. These are the sub-phases of the instruction cycle. So each and every instruction follows this instruction cycle phases. So the first phase is the fetch phase. Fetch phase means we have to fetch the instruction from the memory. Decode the instruction means we have to decode the instruction. Third is the read. Read means the effective address from the memory of the instruction we have to read, that is either in direct phase or the indirect address mode. And the last is the execute the instruction. So there are the four phases of instruction cycle. Each and every instruction follows these four phases. So what is fetch and decode? Basically, the program counter is loaded with the address of first instruction in the program. So program counter, this is program counter. Program counter load the address of the first instruction. PC always hold the address of the next instruction, but in the first instruction the PC hold the first instruction from the program. And the sequence counter, at this time the sequence counter clear to 0, because when we initiate the instructions or we have to initiate the instruction cycle with the first instruction, so at that moment the sequence counter is cleared to 0. Sequence counter is cleared to 0 with the each and every instruction of the computer system. So initially the timing signal is T0. Timing signal is T0 at the time of the sequence counter is 0. After each clock pulse, it has to be incremented with goes to the SC goes to SC plus 1. SC goes to SC plus 1, same as that PC goes to PC plus 1 when we want to execute the next instruction. So PC goes to PC plus 1. At that time, the PC holds the address of the next instruction. And the timing signals are T0, T1, T2 and so on. So the micro operations for fetch and decode phase have the following register transfer statement. These are the register transfer statements, or it known as the RTL. So at time T0, PC transfers to AR. PC hold the address. So that is AR is the address register, that is also known as the memory address register, or it mnemonic is the MAR. Mnemonic is MAR. MAR. PC have the address. Which address? That instruction PC want to execute. That instruction we want to execute. So PC hold the address of that particular instruction. And T1. Time T1. That is the second time signal. That is T0 goes to T0 plus 1. So it is T1. So it is M of AR transfers to AR, and this same time PC goes to PC plus 1. So PC hold the address of the next instruction at the time T1, and M of AR, memory of AR content goes to IR. And the time T2, the instruction has to be decoded. That is D0 to D7 and IR, that is 12 to 14. I define this particular D0 to D7 and IR statements in the next slides. And AR holds IR 0 to 11 because we have, just a minute, you see that, yeah, this is IR. IR have the address bits, these are 0 to 15, that means the 16 bits address holds by the IR, right? This 0 to 11 goes to AR, this define the address of the address of the instruction, and this IR 15 bit goes to I because it is a single bit instruction. So it is I holds only a single bit, so it is 15, and 12 to 14, these are the opcodes. So 12 to 14, that is the opcode. So it decode that instruction. It includes the D0 to D7. I also define that what is D0, what is D1, what is D2, and till D7. So I will explain in the next slide. So just move on with the flow chart of the instruction cycle. This is a very important flow chart of the instruction cycle because each and every step is very well defined and important in the instruction cycle. So we start, so it is sequence counter goes to 0. Each and every instruction we have to fetch, so at that time the sequence counter goes to 0. And at time T0, PC holds the address, that is AR. So it is the address of the first instruction, and at time T1, PC goes to PC plus 1, PC holds the address of the next instruction, and M of AR transfers to AR. That means the content of the address, suppose this is the memory, this is AR, and the value of AR is 0, 0, and the content of this is 1, 0, 0, 1. So in IR, the content of AR, that is 1, 0, 0, 1, transfers to the IR, right? And PC hold to PC plus 1, PC transfers to PC plus 1, that means suppose 0, 1, this is the next address. So PC plus 1 is the 0, 1. So this is the PC goes to PC plus 1 at time T1. These all the instruction covers into the fetch and decode phase. Fetch and decode. That I already explained in the previous slide. So it is T2. This is a decode phase. When we have to decode the operation, so it divides into 3 parts. It is 0 to 11, 12 to 14 and 15. So 0 to 11, it transfers as the address, that is AR. 12 to 14, we have to decode with the opcode, that is D0 to D7, and 15th bit transfers to I. That is already explained in the previous slide, but these are the steps that we have to define in the flowchart of the instruction cycle. Now the D7. What is D7? D7 is the very crucial decoder bit, that is D7. When the D7 is 0, 0, when the D7 is 0, D7 equal to 0, that means when the D7 is 0, that means 1, 1, 1 is not included in the D0 to D7 bits. So when the D7 is 0, so it prefers the memory reference instructions. There are 3 types of instructions, that is register reference, memory reference and input output reference. So when D0 is 0, D7 is 0, D7 is 0 means D7 means 111. The binary of D7 is 111 and D0 binary is 0, 0, 0, D1 is 0, 0, 1, D2 0, 1, 0, same as D7 is 1, 1, 1. So when the D7 is 0 means D7 is absent over there. So means 0, 0, 0 to 1, 1, 0 decoders are present, that is D0 to D6 bits are present. So at this time, these known as the memory reference instructions. These known as the memory reference instructions, right? When the D7 is present, means D7 is high, D7 is 1, D7 is present. So it denotes either register reference or input output reference. I think it is very clear to all of you that D7 is 0, D7 is absent. So it known as the memory reference instruction. When the D7 is 1, that means D7 is high. So it is register reference or the input output reference instructions. So now which one is the register reference, which one is input output reference? So where it cleared by the ith bit. When the ith bit is 0, this is the 15th bit of the instruction. When the I is 0, so it mentions as the register reference. When the I is 1, so it refers as the input output reference. It means that is completely play with the 4 bits. That is, suppose this is the instruction. This is 0 to 11, that is AR, address register. Now 12 to 14, this is D0 to D7, decoding opcode instructions. This is ith bit, either 0 or 1. So when it is 111, when the opcode bit is 111 and ith bit is 0, so it is what? It is register reference instruction. So it is basically 0 111. So it is register reference. Okay. So it is register reference. When it is 4 times 1, 1, 2, 3, 4, 4 times 1. So it defined as the input output reference instruction. Now when the when it is D7 is 0, so it is known as the memory reference instruction, but this is also divided into 2 parts with respect to the ith bit, either it is 0 or 1. When I is 0, so it is known as the direct memory reference instruction. When I equals to 1, so it is known as the indirect memory reference instruction. So D7 is high or D7 is low. When D7 is low, so it is memory reference instruction. When D7 is high, so it is register reference or input output, but it is depend on the bit I. When I is 0, so it is register reference. When I equals to 1, so it is the input output reference. Same in the next side, that is D7 is 0, means D7 is absent over there. That means 0, 0, 0 to 1, 1, 0 is present in the memory reference instruction, but it is also divided into the 2 parts with respect to the ith bit. So when ith bit is 0, so it is direct memory reference. When ith bit is 1, so it is the indirect memory reference instruction. Now this is also read that direct memory address and the indirect memory address instruction that completely done in the first unit. So this is direct memory, means we have to directly approach the memory or we have to directly use the reference of the memory. So there is no operation we have to call. But when the indirect memory address instruction, that is done in the addressing modes. So when it is the indirect addressing mode instruction, so it is we have to directly, we have not directly called the memory, but we have to give the reference of that particular memory. So M of AR hold the address of the AR. So M of AR, suppose this is 100, so it is 100 over there. So the content of AR of this, we have the memory. So this is the indirect memory reference instruction. I think it is clear to all of you now. So I already explained the type of instructions. So there are the 3 type of instruction: memory reference, register reference and input output reference. When the memory reference, so there are also divided into the 2 parts, that is direct memory reference and the indirect. That is completely defined with the ith bit. If the ith bit is 0, then it is a direct memory reference. When the ith bit is 1, so it is an indirect memory reference. But completely the game completely belong with the 4 bits, that the ith bit or the opcode bits, that means 12 to 15 bits. So write down this 12, 13, 14, 15. So when the D7 bit is present, absent, so it is the memory reference instruction. That means it is 0, 0, 0 to 1, 1, 0, and the 15th bit is 0, so it is direct. 15th bit is 1, so it is indirect. So this is the memory reference instruction. Now the register reference and the input output reference when the D7 bit is high, so it is always 111. It is not varied, it is always 111. But the 0th 15th bit is varied, either 0 or 1. So when the 15 is 0, so it is the register reference. When the 15 is 1, so it is the input output reference. Now move on to the next slide. So this is the symbolized form of the instruction, that this is what? D7 complement, that means D7 is low. D7 complement means that is 0, right? And I, okay, and T3. So when the D7 is low, D7 is low means this is memory reference instruction, and ith at this present time the ith bit is 1 because it is simple I, so it is 0 1. 0 represent for the D7 complement, I represent for the ith bit, 15th bit. So it is denoted as a what? It is denoted as a indirect memory reference instruction. When the D7 complement I complement T3, that is nothing, that means it is 0, it is 0, it is also 0. Now T3, so it is denoted as, defined as direct memory reference instruction. I think it is clear to all of you. Now D7 is high and ith bit is either 0 or 1. So when the ith is 0, so it is register reference. When the ith is 1, so it is the input output reference. So this is the type of instruction in the symbolized form. Now we have to move to the next slide. This is the complete description of that. If D7 is 0, the operation code must be 1 of the other 7 values. So it is 000 to 110 that I already explained for the memory reference instruction. Control that expects the value of the first bit, that is ith bit. If the ith bit is 1, so it is known as the indirect address mode of the memory reference instruction. When the ith bit is 0, so it is the direct memory address instruction. So these are the memory reference instruction if the dth is 0. And the representation with the symbolized form in the representation hexadecimal form table. So it is what? When the I is 0, when the I is 0, this is I is the fourth bit, I is the fourth bit, but the 3 bits are 0 to 6. How it is possible? Because it is 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0. D7 bit is absent over there, so it is 0 0 0 to 1 1 0. So this is the memory reference instruction, but the ith bit is 0. The fourth bit is always 0. 0 0 0 0 0 0 0. So it is what? This is represent as 0 1 2 3 4 5 6. So it is 0 to 6. When the ith is 1, when it is same, but the ith bit is 1 1 1 1 1 1 1 1. So it is what? 1 I squared of these bits that we have to count it. So it is denotes as 1,000,000. 1,000,000 that is 8. 1,001 that is 9. 1,010 that is 10. 1,011 that is 11. 1,100 that is 12. 1,101 that is 13. 1,110 that is 14. But 4 times 1 is absent in this particular format. This is the hexadecimal format. So this is memory reference instruction hexadecimal form table. Now, there are the examples of memory reference instructions. So there are D naught represent as the AND operation, D1 represent as the ADD operation, and the operations are M of AR and AC. AC is the accumulator, transfers to AC, the operation resultant transfers to accumulator. Then D1 is the add instruction. Add means we have to add the instruction with the accumulator and the resultant also save in the accumulator. And this is C out, this is the carry out, that is transfers to the enable, that is E. Now the LDA is the next instruction, load the accumulator. STA is the another D3 instruction, that is store the accumulator. BUN, this is the branch unconditional. BSA, this is the branch save and return address, and ISZ. So these are the operations of memory reference instructions, D0 to D6, but D7 is absent over there. So AND to AC. So these are the operations that we have to define in AND to AC. So it is M of AR transfers to DR, and this is the D0 to D4, T4 timing signal, because T3 till T3 we have to decode the instruction, and after T3 timing signal we have to just move on with the either memory reference or the register reference or input reference. But in this example we have to use the memory reference instruction, so we use the T4 and T5 for AND to AC. Now this is the clock cycle form. Now branch unconditional. Branch unconditional means we don't have any condition for transfer the instruction. So when the instruction have defined any rule, so we have to just execute with the next instruction without any condition. So this is known as the branch unconditional. Now branch and save the return address. This is very important, and this particular known as also known as the call and return the save address. So this is known as the subroutine also, or the procedure call. So when it is executed, the branch and save instruction store the address of the next instruction in sequence in memory location specified by the effective address. This operation we have to define by the operation, that is the AR+1 transfers to PC, or PC transfers to, and PC transfers to M of AR. So this operation is very important when we have to execute it BSA. So this is what BSA instruction is always assumed the address of the memory. We have this is the address. We take the example of BSA. Just a minute. This is the example of BSA. This is before the instruction, before execution the instruction. This is after execution the instruction. So before execution the instruction, that is save in the at the address 20, and the instruction is 0 BSA 135. 0 denotes the direct addressing mode. BSA, this is the branch save and return address. 135 is the address, that is 0 to 11 bit, and PC value is 21, that is the PC transfers to PC plus 1. It is hold the next instruction address. When we have to execute that particular instruction, so 135 hold the address of the next instruction. Let's see, when the instruction is executed, then 135 is stored the value of the next instruction address, because after executing that subroutine we have to just move on with the and find the address of the next instruction. So the next instruction we have to give in the address 135. So after save that particular instruction address in the address of 135, that is called in the instruction. So PC hold the value of 136, that is this is AR, this is AR plus 1. So this is also defined in the previous instruction, that PC hold the AR plus 1 value, that is 136 value, and PC hold the M of AR, that is the 21 value. Okay. So this is defined in this, that PC is 136 because AR value is 135, so it is 136, and M of 135 hold the value of 21. This is the instruction of the next address. So, address of the next instruction. So, this is defined in the address part. So, after the execution, the subroutine, when the subroutine is executed, then at which time the subroutine is stopped. So, when this instruction we have to receive at the ending part, that is 1 BUN 135. So, at this present time, the BUN is the branch unconditional. So, we have don't any condition to stop that particular instruction. So, we have to move on with the address, that is 135, and we have to move that particular address. So, we have to receive the value, PC value, that is 21. So, when we receive that particular address, so we have to transfer that address and move on to that particular 21 address, and we have to execute the next instruction, or we have to fetch or decode the next instruction in this particular memory. So, this is the basic instruction of branch and save return address. So, this is known as the subroutine. This is the very crucial topic in the computer organization, that what is subroutine. So, this is the basic example of the subroutine, that this is the before the execution of the instruction and instruction besides in the memory, and this is the after execution of the instruction. So, this is the just theory part that we have to cover, that how we have to process the branch and save return address, and this is the complete defined in the example in the theoretical form, and this is the instruction in the symbolized form. These are the operations that we have to follow, that AR plus 1 transfers to AR. This is basically 136 because the value of AR is 135 in this particular example, and the value of AR M of AR, that is 21, this transfers to PC, right. So, PC value, that is 21 value transfers to M of AR. So, M of AR means 135 memory of 135. So, it is resides, the value is 21 in this case. Now, the register reference instructions. Register reference instructions means the D7 bit, D7 bit is high in this case, but the memory reference instruction D7 bit is low. So, when the D7 bit is high, so 4 bit, that is 12 to 3 bits, that is 12 to 14 bits is always 111. So, first we have to define that the control function that we have to define in the register reference instruction. So, we have to denote with the character value, that is RBI. What is RBI? R is what? R is simplified the IR bit, that is 0 to 11, and it is symbolized by the BI character. R is the register reference, BI symbolized by the ith value, that is 0 to 11, because the I value is 0 to 11 in this case. So, this is the example of the instruction of register reference in the hexadecimal code, that is 7800. This is the hexadecimal code, but in the binary form we have to represent the hexadecimal code. So, first 7 represent in the 4 bits, that is 0, 1, 1, 1, 8 represent is 1, 0, 0, and these 0, 0 represent is the 4 times 0, 4 times 0. So, this is the example of the register reference instruction in the binary form. And D7 bit, because the opcode bit, so it is always high because it is 111. So, this R represent D7 I complement T3. I complement is why it is I complement, because it is 0, and 0 represent the register reference instruction when it is I. So, it is defined through the input output reference instruction. So, it is defined D7 I complement T3, and this denote as R, like that. And this CLA is B11 instruction, so it is B11, otherwise it is BI basically. So, these are the examples. Just see that CLA represent the B11. So, we take the example of this only. So, this is the these are the register reference instructions. So, these are B0 to B11. These are the 12 register reference instructions. CLA, CLE, CMA, CME, these all are the register reference instructions. Clear sequence counter, clear AC, clear enable, complement accumulator, complement enable, circulate right, circulate left, increment AC, escape if negative, escape if positive, escape if accumulator 0, escape if enable 0, and halt the computer. So these all are the register reference instructions. Now these are the input output reference instructions. It is basically R, B, I, but R is equals to D7, I, T4. This is I, R in the input output reference instruction, and these are the basic input output reference instructions. So thank you.